going to continue our discussion of the multiple regression model, but with a twist this time. And the twist is that instead of having x variables that are continuous variables, we will consider situations where the x variables are actually categories. Okay, so let's now go into this and consider this situation with an example. So the example is that we are trying to figure out if there is salary discrimination between male and female employees at a bank. And this bank is named Mythical Bank. It's called Stag Bank. And so I have provided 4 different Excel files for you, named Stag Bank 1, Stag Bank 2, Stag Bank 3, and Stag Bank 4, with more and more data that we will be using for our analysis. Now, this data considers not all the employees of the bank, but it's a sample of 208 employees at the bank. And we would like to know if there is gender-based salary discrimination, and we want to use a regression model to test whether discrimination exists or not. Now, if we have to come up with a regression specification to do that, obviously the y variable should be the salary, right? But then the question is, what should be the x variable that we should look at? Now, that may not be immediately very obvious, but if you think about it, really we want to see whether gender affects salaries, right? But gender is male or female, and so it is a category. It is not a continuous variable, right? So a continuous variable can take several values in a range, but a categorical variable is not like that, right? And in this case, since we have got 2 categories, male and female, we can use one dummy variable or binary variable to capture these 2 categories, right? And this dummy variable can take 2 values which are coded as 0 or 1, right? And and we can assign 1, let us say for the females, and 0 for the males. Now, it doesn't really matter if we had done this assignment of the dummy variable the other way around. All our analysis and our results from the regression will still be the same, okay? But for our purposes, we have taken gender dummy variable to be equal to 1 for females, okay? Now, if we have more than 1 categories, we can still use them as part of our regression specification. But then in those situations, instead of having just 1 dummy variable, we will have n-1 dummy variables for n categories. Okay. So as we move ahead in this lecture, we will also consider an example of that type. Okay, but for now, let's consider only this category of male and female. So just 2 possibilities there, right? And so we will need only 1 dummy variable. Now, there can be many other examples that are relevant in business situations. For example, you might be considering purchase behavior of new versus existing customers, right? So in those situations, you can take number of purchases, for example, as your y variable, and the new versus existing customer are categories, so you can use a dummy variable to capture these categories. Similarly, you can think of trying to relate the purchase behavior of customers exposed to ads versus those who are not exposed to ads. So once again, we have the purchase behavior, the number of purchases as the y variable, and the x variable is dummy variable, which captures whether we are thinking of the customer as the category which are exposed to ads versus not. So again, we can have a 0, 1 to capture that difference between the customer types, right? So now moving ahead and considering the model that the salary is our y variable, and then that is equal to beta 0. plus beta 1 times gender dummy plus epsilon, right? That's our, the model. And we can quickly run a regression on that with the specification of the gender dummy that we have talked about. And if we run this specification, this is the parameter estimates table that you will get. And you see out here that the coefficient of the gender dummy variable is negative. It's a negative 8.296. And the p-value associated with this variable is very small, right? It is less than 0.0001. So of course it is less than 0.05. And so one can conclude that the gender dummy variable is statistically significant, which means that whatever we are seeing is not only limited to the sample, but rather it is very likely that it extends, this relationship extends into the population of employees. Okay. Now, clearly, we can see that if you are a female employee, then on an average, such employees will have a lower salary, right? Because of the negative coefficient of the gender dummy variable. Remember that we specified the gender dummy variable to be equal to 1 for female employees, and for male employees, it is equal to 0, right? So that is why the average salary of male employees is $45,505. And the average salary for female employees is $45,505 minus $8,296, right? So this is, at least the regression does tell us this much. But is this evidence for discrimination? And the answer to that is a little nuanced. The answer is no, actually, right? It is clear that the salary for females is lower, but that does not mean gender discrimination. Why? The reason is that, for example, you may think of that the difference in salaries between males and females is not because of the gender difference, but because, for example, female employees have lower experience on an average compared to the male employees. And if the hiring has for the female employees has picked up in the recent years, then it is likely that the female employees are on average younger, and so it is they are getting a lower salary, but it is not because of gender differences, right? So we cannot really say that it is gender difference that's driving the salary difference. So how do we take care of this possibility that maybe the male and the female employees are different in terms of their experiences? Well, the quick way, the best way to do that is if you have got experience data, if you've got data about how many years of experience every employee has, then you can extend your regression specification by adding an experience variable out here, right? And turns out that we do have this data, and this data is presented to you not in the StackBank1 file, but in a different file. And once we use the experience data and once again do this regression, you will see that you will get a slightly different result. Now the estimated salary turns out to be 35.8, right? So this is in thousands of dollars, minus 8.0 times gender dummy, plus 0.98 times experience. So clearly what has happened is that by including the experience variable in the specification, right, the coefficient of the gender dummy variable has changed and it is actually reduced, right? So once we account for experience, then we can see that there is still salary difference on an average between male and female employees. But now this salary difference has become lesser, right? If you remember from the last specification, it was $8,296. But after accounting or controlling for experience, only 8,000. So now, what we can say is that clearly, the salary difference is still there, but after controlling for experience, it is not as bad. This difference is not as much. Okay. Now let's ask a follow-on question. And this follow-on question is, that yes, we can see that experience matters, and more experience leads to more income, more salary. This is actually clear from the parameter estimates table on the slide here. You can see that the coefficient of the experience variable is positive and statistically significant, right? But can we answer the question that is the salary, does that increase at different rates with experience for males and females? Can we actually answer this question using the regression specification that we were just looking at? So maybe take a pause at this point and think about it, and then come back and watch the rest of this video. So the answer to this question is that you cannot really figure out whether salary increases at different rates with experience for male and female employees. You will have to extend the regression specification by adding yet another term to it. And this term is the interaction term. And such an interaction term is created by multiplying the gender dummy variable with the experience variable, right? And this interaction variable is shown in the StackBank3 file. So let me go here and show you this file. So this is the StackBank3 file, and you can see that we have got data in column A for the employee ID. The data in column B is the gender as male or female. In column C, you have salary in thousands of dollars. Column D now contains the gender dummy variable that we have been talking about. And this gender dummy variable is quoted as 0 for males and 1 for females, right? And then in column E, we have experience in number of years, right? And finally, in column F, we have the interaction variable, which is created by multiplying the dummy variable and the experience variable. So you can see that since the dummy variable for males is always 0, the interaction variable value for males will also always be 0. You can see this from your row number 2 out here, right? And you can also see this from, let us say, row number 6 out here, right? So once again, because you have a male, the interaction term would be a 0. For all the female employees, this interaction variable would actually be their experience, because it is experience times gender dummy, which is equal to 1 for females, right? So now we have created this interaction term out here, and now we will run the regression by including this interaction term, okay? And so here is the regression after we have included the interaction term, and you can see that the outcome that we get is that estimated salary is 30.43, that's your intercept, plus 4.1 times gender dummy, plus 1.53 times experience, minus 1.25 times the interaction term, which is gender dummy times experience, right? All of these coefficients are significant, so all of these matter in a statistical sense, right? Now let's move on and see that how can we interpret this interaction term? How can we interpret the coefficient of this term? And how does this interpretation help us in answering the question that we had raised, which was that does the salary of male and female employees change at a different rate with experience, right? So let's use the regression specification that we came up with and use it to write the estimated salary separately for males and for females. So when we want to write the estimated salary for males, we can plug in the value of the gender dummy variable as equal to 0 in the equation that we see here on the slide. So when we do that, the second term will become 0. The second term is 4.1 times gender dummy. So that term will become 0. And the last term, minus 1.25 times the interaction variable, will also become 0 for the males. So our estimated salary equation for males turns out to be 30.43 plus 1.53 times experience. Now let's do the same thing for the female employees. In this case, the gender dummy is equal to 1, and let's therefore plug in this value into the regression equation that you see here on the slide. So now the second term will no longer become equal to 0 because gender dummy is now 1, so the second term becomes just 4.1, right? So what that means is that the intercept term is not 30.43, rather it becomes 30.43 plus 4.1. So for females, therefore, the intercept becomes 34.53 instead of 30.43 that we had for males, right? Now let's look at the last two terms. The third term still is 1.53 times experience for female employees, but the very last term, the fourth term, is minus 1.25 times experience, right? Because it does not become 0 in this case. And hence, when we take 1.53 times experience minus 1.25 times experience, we are left with 0.28 times experience, right? So that gives us the equation for the salary for females. Now, let's say we plot both of these equations on a graph where we have experience on the x-axis and salary is on the y-axis. Now, clearly you can see that at experience values that are closer to 0, okay, that are towards the left, you can see that males may actually have a lower salary, right? And females will actually have a higher salary. However, as the experience increases, the rate of increase of salary for males is higher than that of females, right? And that is why the coefficient of the experience variable is higher for males, it's 1.53, as opposed to this coefficient being 0.28 for females. So what that means is that once an employee gains sufficient experience, then a male employee then may have a higher salary on an average compared to female employees, right? So the answer about discrimination is not so straightforward. Really, it can be more nuanced like this, right? And we would not have discovered this until we use the interaction variable of gender dummy and experience. Okay. Now let's move further and raise this question that we had raised earlier in the context of experience. We had said that maybe on an average the female employees have a lower experience, and that is the reason for their getting lower salaries. And then we took care of that problem by including the experience in our regression specification. But experience may not be the only variable that in which the females and the male employees may differ, right? They may differ on other factors as well, which also may drive a salary difference, right? So another possibility is the job grade of the employees. Now, employees who are in a higher job grade are likely to get a higher salary than employees who are employed in a lower job grade. Now, if the situation is that male employees are typically on an average employed in higher job grades than female employees, then once again, we expect a salary difference between these two categories for this reason rather than a gender difference driving a difference of salary, right? And remember, discrimination exists only when we can prove that it is only gender difference that's driving the difference of salary and not any other reason, right? So if we suspect this, then just like what we did for experience, we have to include the job grade as part of our regression specification to account for this suspicion that we have. So let us say that this job grade, now there are 6 different job grades that are there in this bank, right? So these job grades are numbered 1 through 6. Okay. Now, of course, we cannot directly take this job grade variable as 1 through 6 in the specification. Rather, we want to, because there are 6 different categories, and so we want to create 5 dummy variables. Remember, 1 less. There are 6 categories, so 1 less dummy variable would be used. So we will want to use 5 dummy variables to capture these 6 job grade categories. Okay, and the way that we do that is as follows. So you can see on the slide here that we have got these 6 job grades, and we created 5 dummy variables named job grade 2, job grade 3, job grade 4, job grade 5, and job grade 6. Now for the job grade 1, the value of the dummy variables for all of these 5 variables is 0, right? So the job grade 1 becomes our reference or baseline category. Now job grade 2, for this job grade, the job grade 2 dummy variable is 1 and the rest of them are 0. For the job grade 3, the job grade 3 dummy variable is equal to 1 and the rest of them are 0. And so now I guess you would have understood that how the job grade dummy variables are given values corresponding to each job grade of the employee. So this information is available in the StackBank4 file, and you can actually work with that to run the regression, right? And now the extended regression model that we want to use is salary as the Y variable. And now, in addition to the terms that we were already having, we would add 5 more terms, 1 for each dummy variable, right? And we can run the regression with this extended specification, and this is what we get to see. All of our coefficients turn out to be significant, but let's now focus on the job grade variables. You can see that job grade 2 variable is significant with a coefficient estimate of 2.596. What does this mean? How do we interpret this? This means that compared to job grade 1, an employee in job grade 2 earns a salary that is higher by $2,596 on an average, right? Now let's try to interpret similarly the coefficient of job grade 3. So what does this 6.22139, what does this mean? Well, once again, remember our baseline category continues to be job grade 1. So, and when we say job grade 1, remember that the value of job grade 2, 3, 4, 5, and 6 dummy variables is all 0 for an employee in job grade 1, right? So if you want to interpret the meaning of job grade 3 dummy variable, what that means is that an employee in job grade 3 earns a salary that is higher by $6,221 compared to an employee in job grade 1 on an average, right? And so this is how we make use of categorical variables in the regression, right? And this use of these categorical variables can be very useful in many real-life situations when we are working with categories. Now, one difference that I want to point out is that all of these are situations where the X variable is a category, right? We have not talked about a situation where the Y variable is a category. That can also be done, but that cannot be done with using a simple regression kind of a approach that we have been using. Different kinds of regression models are used to capture those situations. Okay. Now, some final thoughts about the dummy variables. Suppose you ask, can we have a regression with all the X variables as dummy variables, right? Maybe we don't even have a single X variable that's a continuous variable. Is that possible? The answer is yes, that's very much possible. It's not necessary to have all the X variables or have any x variable as a continuous variable. You can have all x variables as dummy variables. Okay. Now moving on to the interaction terms. Right now in our example, we saw an interaction of the gender dummy with the experience. So one of these variables was a dummy and the other variable was a continuous variable, because experience can be 2 years, 5 years, 10 years, 12 years. So it's a continuous variable. So if the question comes that can we create an interaction by multiplying two dummy variables? The answer is yes. It is perfectly legitimate to create an interaction variable by multiplying two dummy variables. Okay. And of course, you can create an interaction variable by multiplying a dummy and a continuous variable too. Okay. Once you do that and run your regression, and if you find that the interaction, the coefficient of the interaction variable turns out to be statistically insignificant, what that means is the interaction does not really matter, so what you should leave out this interaction term from the regression specification.